Our next speaker is Anthony Brady, who just defended his PhD thesis recently, and he was advised by Ivan Aguio, and he's going to tell us about, I believe this is his joint work with Ivan on stimulating quantum aspects of an analog white black hole.
Okay, perfect. Thank you, Mark. So again, my name is Anthony, if you haven't met me before. So let me just get started. This is stimulating quantum aspects of an analog white black hole. This is something that is currently in preparation, not completely finished yet, but getting there. And as Mark said, this joint work with a fellow grad student, Dimitris Kronos, and our fearless leader, Ivan Aguio. And if I had to say what we do in sort of two sentences, we do a bit more than this, but in two sentences. So we study this Hawking pair creation mechanism, and all these italicized words are hopefully words that I'll explain more clearly as we go along. So study the Hawking pair creation mechanism in a toy model for an optical analog white black hole scenario, and propose a method to enhance entanglement generated in this Hawking pair creation mechanism, and also to overcome background effects. Okay, so hopefully I'll explain that as we go. Okay. So just an overview of the talk. So, I said something about the Hawking effect, and this is, Hawking radiation related to black holes and stuff like that. So I'll really start the talk off in the mid-70s with Hawking's calculations about evaporating black holes, which led to this famous information loss paradox, which has been a puzzle for theoretical physics for the past 45 to 50 years. So this will sort of set the relevance and context of the research. And then I'll move on to say that, even though this was originally derived in the black hole context, it appears to be a universal effect, like a general phenomenon that occurs in many other different systems, not just exotic black holes, but also in fluid, BECs, dielectric medium, so on and so forth. And so from there, we'll move on to a specific medium and a specific model of a medium. In particular, we'll study an optical analog using a toy model, which is like a Lorentz oscillator type model for a dielectric medium. I'll discuss some prior results derived by others, which derived Hawking radiation in this medium for an analog black hole, and then go on to discuss our recent results about an analog white black hole and some interesting things there. Okay, so let me get started, get into the meat of the talk and some serious business. So I'll start in 1974, this famous letter by Stephen Hawking, Black Hole Explosions. So what he showed in using quantum field theory on a classical background spacetime is that black holes are not totally black, so they don't just absorb radiation and matter. They're actually black bodies which emit thermal radiation with characterized by temperature entirely characterized by temperature. The emission products are now known famously as the Hawking temperature. And this is an interesting formula because you see like all the constants of nature except for a charge appearing here. We have Newton's this 8 pi g sort of comes up in Einstein's equations, Boltzmann constant h bar and the speed of light c. And then we have the open parameter here m, which that's the mass of the body which collapsed to form the black hole. And I just want to note for, like decently sized black holes, this is very small. So this is edging on the side, on the temperatures around nanokelvin, about 100 nanokelvin. So black holes, so that's kind of interesting thing there. Black holes are not black, but emit radiation. The radiation has to come from somewhere. It's coming from the mass of the black hole. And so as it emits radiation, the black hole loses energy and loses mass. And obviously this can't go on forever. And so eventually, if you just sort of use semi-classical approximations, this thing should evaporate completely. And you can, for example, estimate a lifetime over which this process should occur. And it's about 10 to the 6, 7 years compared to the 14 billion year age of the universe. In any case, this is quite interesting. Applying quantum fields on a background for space-time showed that black holes spontaneously emit thermal radiation and eventually evaporate. And this causes some issues. So this is sort of the root of this information loss paradox we're all talking now. So if you take the evaporation process seriously, this presents some issues, and this was pointed out in particular in this follow-up paper by Hawking in 1975. Okay. So I'm just going to go through some, little tidbits from the paper and try to bring out some essential features of this information loss paradox and highlight them with very simple equations. So first, let's start off. This is a very illustrative diagram. What I have here on the right is a Penrose diagram for a body which is collapsing to form a black hole. And what a Penrose diagram is effectively is just it's the entirety of the space-time that just compacted into this finite region, which you can write neatly on a sheet of paper. And the nice thing about this is that it maintains the causal structure. So, for example, light rays move on 45-degree angles. And there's 3 of these little null surfaces here. They're null because they're 45-degree angles, which we want to point out. First is this so-called scry minus, scry for script I, scry minus. This is like a past null infinity before the body collapses. And this is where light rays originate from. We have scry plus, which is the exterior to the black hole, and this is where light rays end up. If they do not fall into the black hole, if they do not fall go through the event horizon, which is here, and fall into the black hole. So notice that the event horizon is it's at 45-degree angles as well. And this is this notion that you can't escape from event horizon once you fall in, because any light cone that I put within here will remain within there and eventually reach the singularity, which is this jagged region. Okay, so I'm going to try to go through these quotes and align with some notion of why there's some information loss or some puzzle going on. Okay. So firstly, so the interaction region can be bounded not only by an initial surface, this is the scry minus that I said before, on which data are given. So for example, an initial quantum field given on here. And so that'll be represented by this Hilbert space, which has this of index with scry minus. So not only bounded by an initial surface on which data are given and a final surface, scry plus. So this is this final surface associated with the observer's exterior, the black hole, on which measurements are made, but also a hidden surface, H, this is the horizon, about which the observers have only limited knowledge, such as the mass, angular momentum, is charge. And so really when I interpret this, what I say is, is that really what we have here is we have some initial surface, some initial Hilbert space, and then we have this decomposition of the Hilbert spaces in the future. And it's really causality induces this decomposition, okay? And the reason being is that if I, for example, if I give data only here, I can only propagate it back and cover this region of space-time. I don't have anything in the interior of the black hole. So therefore, I need to give data here and here as well in order to cover the entire space-time, and that's this Hilbert space decomposition. Okay. The second step is really, related to this 1974 paper. The surface emits with equal probability all configurations of particles compatible with the observer's limited knowledge. This is just the statement that the black hole spontaneously emits radiation, and then it's completely incoherent and thermal and only characterized by one parameter, which is the temperature, which in the case for a Schwarzschild black hole only depends on the mass. And so this is a thermal state with a mean number of photons in bar, and has a spectrum which is Planckian. So it's not only a thermal state, it's Planckian distributed according to the Hawking temperature. Third statement, probably this is really the most important statement that we need to keep in mind, I think, is that, so it makes this statement: black holes create particles in pairs, with one particle always falling into the hole and the other possibly escaping to infinity. Effectively, what this is that, first in the second step I have here, I've shown a transformation from the vacuum state here to a thermal state on Scribe Plus, you should say, oh, hold on, obviously that's not unitary, but that's fine because, like I said, I'm not describing the entire Hilbert space with just this transformation. And I sort of do a unitary extension and go to the entire Hilbert space. What I do have is some unitary map, and that particular unitary map is exactly what Hawking is saying here, is that the black hole actually creates particles in pairs, with one part of the pair going to Scribe Plus as a thermal radiation, and the other is associated with these horizon modes, which on the horizon or fall into the black hole. And just by the way, if this is a bosonic field, then this is just a two-mode squeezed vacuum state. Okay, so that's the relevant things that we need to keep in mind. These Hilbert spaces, thermal radiation, and this coherence here. Okay, so this is where some issues start to arise. Okay, so with this sort of picture in mind, then we start thinking about evaporation and where issues come up. Okay, so the issue here is that the metric, the space-time metric, the gravitational field is the source of this amplifier. I didn't say it here, but I mean, this is really an amplification, a generation of particles, right? So the gravitational field is the source of the amplifier via the mass m. Okay, but m decreases with time because the black hole evaporates, and eventually it will go kaput in some finite amount of time. The rub is that if one trusts Hawking's calculations all the way through this evaporation process, through the entire process, this mapping from Scribe minus to Scribe plus is always this, it's non-unitary, it's always this sort of amplifier channel. But simultaneously, these horizon modes, which you could think of, we use to purify the system, seemingly vanish. So when the mass of the black hole goes to zero, the horizon vanishes as well. And we're left, it seems, with only thermal radiation on Scribe plus and with nowhere else for the information or for the quantum coherence in our initial particle pair state to go. So that leads to the $1,000,000 question, is where did the information stored in sort of these horizon modes go? And this is resolving that is effectively resolving the information loss paradox. I just want to point out that it's, it seems like general relativity is the problem here. And, there are several ways to approach that people go about and have been trying to go about resolving this puzzle, but it's stood strong for almost 50 years now. And it seems to me, at least, that we need sort of a theory of quantum gravity to resolve this. Okay, so that's the, fundamental physics, theoretical context of the information loss paradox. So I want to say that, information loss to a black hole is, from my view, it's magnified by the Hawking effect, but not necessarily a source of it, and may require quantum gravity to resolve. However, the Hawking effect actually turns out stands on its own as a more universal and generic phenomenon, and is really associated with formation of an event horizon, no matter how that event horizon is formed. Okay, and there's this nice paper by Matt Visser which goes over this essential features of the Hawking effect. So I'll just sort of define what the Hawking effect here is the following. So it's a particle pair creation mechanism. So you can think of it as a two-mode squeezer if you want. Whereby particles are created in pairs via, so the mechanism is here, the formation of an effective event horizon and an underlying geometry. So this is, horizon-induced particle pair creation. This is the Hawking effect. And so what is this telling us, at least from my perspective, what it's saying is that these causal barriers are quantumly unstable. So horizons spontaneously decay. So why is this, in what respect does this come up as a universal or anything like that? Well, it actually sort of, you can maybe argue it as a bit before this, but really in this paper by Bill and Rue, it showed that, this particle pair creation by the formation of the horizon is more general. Okay, so this is a famous paper in 1981 where Phil and Rue show the formation of a sonic horizon in a classical fluid induces particle pair creation. So we have just a little illustration is we have some fluid and that has some background flow. It's rightward is downstream. And to the left, we have, the flow of the fluid is less than the speed of sound. So little fishies or sound motes can propagate downstream. They can propagate upstream just fine. However, as we move rightward, the speed of the fluid increases until a point where it reaches the speed of sound. And afterwards, it's greater than the speed of sound. And so if little fishies, flow past this region, they can't flow faster than the speed of sound, unfortunately, and are swept downstream and cannot flow back upstream. So this region here actually demarcates the boundary of an effective event horizon. Bill and Rue showed that if you actually form this in classical fluid, it's not just an analogy. If you form this, then at least in principle, this thing should emit particle pairs and have an associated Hawking temperature with it. Okay, so let me move on. And since then, there's been analogues abound. So since that sort of 1981 paper, there's been the Hawking effect and tons of other systems, bosons and condensates, classical fluids, like I just mentioned, optics, and experiments in all of these systems as well. I just want to point out just my quantum information science friends that actually the original paper on Bose-Einstein condensates, this CZ here is Serac and Zoller. So they actually put out this paper, the first, in principle, saying that you could form event horizons in Bose-Einstein condensates. So I just want to say, so the Hawking temper has actually been measured in the classical fluid case and also BAEC analogues, though no entanglement for these pairs that are created has been observed to date in any platform. And that would sort of be like the ringer. Okay, so what we'll focus on from here out is these optical analogues. Yeah. So optical event horizon, how do you generate an effective event horizon in optical media? Where, well, you use this, this so-called Kerr effect in the co-moving frame. So what I mean by this. So firstly, there's two things you need to do to generate, to sort of induce this Hawking effect. You need an effective background geometry, which dictates mode propagation. This is just given by the refractive index, the dispersion relation. And so I have a picture of here, where we have some medium, and exterior to some region, we just have some dispersion relation, which gives you this mode flow. And this, let me. And the second thing we need to do is need to form an effective event horizon, which restricts the mode flow, okay? Which effectively restricts the mode flow to sort of one direction, only propagating downstream as in the classical case. And we can do this via the so-called Kerr effect. So what the Kerr effect is, it's effectively a perturbation to the index of refraction, where this perturbation is dependent on the intensity of a pulse, a very strong pump in the medium. So what I've drawn here is a sort of traveling perturbation, a pump. And so what we do, we go to the co-moving frame that defines your effective background flow, okay? And so very far away from the pump, you can have flow of modes downstream and upstream. However, as you approach the pump, there's this region where only downstream propagation is permitted. And what's interesting about these setups is that the setups actually admit a black hole event horizon and a white hole event horizon. The white hole is sort of like a black hole turned inside out. So the black hole is, nothing can escape, nothing can go out here. But the white hole is everything escapes and nothing can actually enter. So you can think of it in this case, for example, this mode is trying to catch up with the propagating pump, but as it approaches it, it can't cross it, and eventually it slows down. Okay. So moving on, this is just the little fishy picture of exactly the same scenario. It's sort of like a ramp up and ramp down of this flow profile that's forming these horizons. Okay. So I just drew pictures and said there's the analogy, but you should be wondering, well, how good is this optical analogy? Is there something of merit there at all? And it seems to be the case that there is. So there's been some, for example, at least in this paradigm of nonlinear Maxwell equations, there's some suggested numerical studies that suggest that there's amplification when this horizon is formed and that a horizon is formed. There's also been some experiments, particularly by this guy named Ulf Leonhardt and his members, suggesting the formation of an event horizon and also measurements of the stimulated Hawking radiation. However, no Hawking temperature has actually been measured yet, and that's sort of you have to take these experiments, be a little skeptical. And so, from a theoretical side, well, I just want to say that, sort of providing a quantum theory for this Hawking process, this paradigm of nonlinear Maxwell's equation seems a bit challenging. And this has actually led to some effective models or phenomenological models where, for example, the matter degrees of freedom are addressed directly, as opposed to the nonlinear Maxwell equations case. And in particular, I want to focus on this Lorentz oscillator-like models, which I'll get into in a second, where some analytic results have been derived exactly. And I'll focus on this paper by Linder, Schutzhold, and Unruh in 2016 again. I'll just call it LSU from now on. So LSU 2016. Okay, that's actually the year I entered grad school here. All right, so here's the model that they consider in their paper. So effectively, it's just that it's a 1+1 dimensional model and an electromagnetic field coupled to a continuum of oscillators. And so this is a Lagrangian for the setup. So this is the electromagnetic field where A is the vector potential. So this is the free electromagnetic field Lagrangian, free oscillator Lagrangian, and this is this is more or less just like a dipole coupling. Okay. And this is an effective model in the sense that the effects of the nonlinear background pulse are actually just wrapped up in this coefficient, this oscillator frequency. And it's traveling sort of with the pulse. So you can imagine there's a background pulse traveling and it's locally changing the spring constants of the and just you can compare this to your simple point like dipole coupling. And just to point this out, you can derive, for example, like a Sellmeier relation, which gives you the refractive index of the medium from this model, and it's given, for instance, by this. This determines the refractive index and the modes allowed in your system. And so, for example, this is a model with only one medium resonance. Okay, so just going forward, so what these authors really look at is so the dispersion relation and scattering in the co-moving frame, as I mentioned previously. So the underlying geometry here is effectively this dispersion relation in the co-moving frame, which defines the normal modes of the system atop the background flow. So what I have a picture here is, this sort of, you think of a pulse is actually traveling to the right, but when I go to the co-moving frame, it's like things are going to the left, and that gives the background flow. If you find the dispersion relation in this frame, we find is that far away from the pulse, you can have all of these upstream and downstream modes. However, you can actually induce, this it's what seems to be an event horizon by introducing like a profile here, where as you enter into this region, only downstream modes are permitted. And so, in this paper by Linder, Schutzhold, and Unruh, they consider, for example, only like a very simplistic model of a linear profile. And so, this is some prior results that they had. So under this assumption of like a linear profile for this traveling index perturbation, they derived, for example, the outgoing Hawking flux, so the emission of this effective horizon that forms analytically and directly. So this is, for example, the outgoing mode relation. It's just a Bogoliubov transformation from the in modes, which propagate inwards here to at least one of the out modes, which makes it out to the exterior of the black hole. And notice that one of these modes has a dagger on it. And this is indicative of particle creation. Okay, so what they derived really is this is sort of what all of these papers are focused on, is deriving this so-called Hawking flux of the number of particles that reach out to infinity if I just initialize in the vacuum. And so this is thermal in character, or Planckian in character, up to some gray body corrected factor, which actually this appears in the astrophysical case as well, and just comes from an effective barrier that the outgoing Hawking radiation must go through in order to actually come out. So the caveats, however, is they didn't actually derive the full scattering picture. As I've noted here, this is just like a 3-to-1 mode relation, right? So I have 3 in modes, I have 1 out mode, so they didn't actually derive the full scattering picture. The second thing is that this is a completely non-realistic profile. I mean, they considered a linear ramp and completely ignored actually the white hole side. And so this is where we step in, we give, actually provide ansatz for the full scattering picture in the linear ramp case. This is inspired actually by the Bloch-Messiah reduction for quadratic interactions, because I showed the Lagrangian before, didn't mention it, but it's a quadratic Lagrangian, so you can apply this Bloch-Messiah reduction.
Anthony, you have about 4 minutes, okay?
Yeah, that's fine.
All right.
Thanks, Mark. So we also so that's just a minor step. We also generalize to more realistic background pulse profiles. So sort of a leading edge and a trailing edge, which is a white hole and a black hole that share an interior region. That's what I showed before. And this is the white black hole that's in the title of my talk. And we also provide the extended ansatz for the full scattering picture. Under this, we also give quantum correlation. Given this full scattering picture, now we can look at a lot of different things. So, for example, one thing we look at is entanglement generation by the setup, and for example, in the midst of thermal effects and everything else. And I just want to mention that these white black holes, they've been considered in the literature. They actually were discussed in the Serac and Zoller paper, but to my knowledge, no correlations or any of this sort of full scattering picture has been detailed in any context. So, okay, so here is the scattering picture. I'll just put it on the screen. This is actually the full scattering picture, and will give us back, for example, this Hawking relation. So what we have here is we have a 2-mode squeezing. This is a 2-mode squeezer, this little element S. And this is the Hawking pair creation mechanism, where particles are created in pairs and are thermally distributed. And I hear somebody in the background with their microphone. Okay, and so this is the full scattering picture, and we actually include gray body effects here, which is really just a beam splitter. And this is nice because it actually gives us an equivalent picture to the intuitive picture that one might think is of modes traveling inwards, pairs being created. As the Hawking radiation goes outward, it meets a barrier and either scatters back into the black hole or comes out to infinity. Okay, so again, this is a nice thing because there are a bunch of equivalent pictures going on between the sort of mesoscopic physics here to the intuitive picture. And this Bloch-Messiah reduction really tells us that all of these pictures are equivalent ways of speaking of the same thing. So this is a very simple diagram, but it comes extremely useful, especially when we extend it to a white hole and a black hole. So we extend these results to a pulse with a leading edge and a trailing edge, and using some knowledge that the white hole process is actually just the inverse of the black hole process, or equivalently just using some symmetry arguments about the center. We can construct a similar sort of optical circuit for this case as well. And this is where the Bloch-Messiah reduction comes in handy, because this is a slightly more complicated circuit that I've drawn. So on this side is the black hole scattering process, and on this side is the white hole scattering process. And notice I have a little inverse for the white hole scattering process. So this gives us actually a very clean way to address the problem, look at various scattering mechanisms precisely, and also to look at how particles and correlations are flowing throughout between the modes and throughout the system. So, for example, there's it's clear that the particle creation of the black hole actually seeds the white hole particle creation. So these are the outputs of the black hole. This bottom one falls into the interior and actually reaches the white hole event horizon and then seeds the particle creation mechanism there. So that's one thing we do. Another thing we do is study quantum correlations, and we do it using this PPT criteria, which is a criteria for entanglement. For our system, it's actually a necessary and sufficient condition for entanglement, and so we study entanglement conditions there using this criteria. So for example, we analyze.
Yes. Sorry to interrupt. If you could wrap up, we hit the time. I think it's
okay.
good for us to have the full break time.
Yeah, that's fine. Just give me one more minute if you don't mind. So yeah, this is the next thing we look at this entanglement conditions, assuming, for example, stayed initially at thermal equilibrium, and this PPT criteria gives us conditions on the Hawking temperature in order to observe entanglement in the system. This is last slide here. So we also look at single mode squeezing at the input to enhance entanglement and actually overcome these background temperature effects. And so I won't discuss a summary of the work, but I just want to say that these optical platforms actually seem particularly suited to the task of observing quantum correlations and analog Hawking effect. With experiments, really because this is sort of the thing in quantum optics. This is what a lot of people in quantum optics do. So, for example, you can measure covariance matrix via this double Hammond measurement scheme and so on and so forth. And this is just an interesting project. There's a lot of cool physics in it. And yeah, that's all I want to say. Thanks.
All right. Thanks a lot for that. We'll take a break now.